Hi, my name is Carlo and I'm going to present you the work that I've been doing throughout my master thesis. But first of all, I want to thank the organizers of the third symposium on algorithmic information theory and machine learning. And I also want to thank Pedro, the PhD fellow that invited me on this project. Yeah. So first of all, I will present the motivation, then the MoMos framework, that is the first method that actually uses Kolmogorov complexity to compress neural networks. Then I will show some study on MoMos. I will present a technique I developed on top of MoMos, and then I will show some generalization bounds on MoMos using the VC dimension. So motivation, in recent years we have seen neural networks being over-parameterized, and for example large language models keep scaling. The number of their parameters doubles every 6 months. We have seen the first model of trillions of parameters some months ago, maybe in February, I don't remember. And yeah, this scale up in the number of parameters implies a higher compute, memory, and energy consumption. We are going to tackle especially the memory, and we hope that in future work we will be able to expand the memory reduction into energy and compute reduction. The thing is that in the literature it is shown that when models scale up so much, it is possible to prune them or quantize them, reducing the size of the neural network by hundreds of times without achieving the same accuracy or the same metric, performance metric used to evaluate the model. Another interesting fact about the technique I will show is that it is employed throughout training from the very first epoch. And so we are bounding how big the model is from the very first epoch, and we just keep simplifying it throughout the training, as we will show. So the Kolmogorov complexity is the length of the shortest program that outputs the object x, and we are going to use this definition. Note that it is uncomputable per se. You can reduce it to the halting problem. In my thesis I proved that it's uncomputable, but there is some approximation of the Kolmogorov complexity. In particular, there is BDM that is developed. There is BDM, and BDM was applied to neural networks for the first time by Edward on binary neural networks, but they don't scale up very well. No, it's not that they don't scale up, but this technique doesn't scale up very well, and it's less accurate if you use it on neural networks that are not binary. That is why the PhD student that followed me introduced quantized BDM, so that you apply it on different bits of you basically quantize the weights, and then you use BDM on different hyperplanes of different bit depth. Okay. The Kolmogorov complexity is interesting also because it tightens the generalization gap. Long story short, basically if a model is simpler, the loss that you predict on a small and finite data set is more precise. The bigger the model, the bigger the discrepancy there can be in the loss. That's Yeah. And finally, and most importantly, the Kolmogorov complexity bounds the description length of a model, which means that if we are able to find a good way to describe the model, we can save a lot of bits to store it. We save also a lot of electricity when we share the model, and yeah. So MoMos framework. MoMos stands for Mosaic-of-Motifs. It is a technique similar to vector quantization in practice. And so given a vector, so a neural network can be parameterized through a vector, through a vector of parameters. MoMos split the vector into blocks. Then it samples some codebook, some motifs, and to reconstruct the original neural network, you also need a mosaic, which are the index that are used to reconstruct the original vector. So, for example, 1 says the first motif is used in the first block of the original vector. 3 means that the second block used the third motif. 2 means and so on. To parameterize Z and then, the number of weights inside each motif is called block size, while the number of motifs is k, while n is the number of parameters and n is the number of blocks. So m is given by n divided by s, so number of parameters divided by block size, so how many weights there are in each block gives how many blocks there are in total. Yeah, we have seen this. We are going to use HSK to refer to the hypothesis class induced by the MoMos parameterization. Note that if we have Z and M, then the codebook and the mosaic, then we are able to reconstruct the original vector. But we also need to store the inverse slicing operator, which actually is a constant size procedure. So asymptotically, its value is going, it's not relevant. And in this way, we are bounding the description length of the vector. And note that otherwise, the description length would be n times q. So the number of bits, q is the number of bits to describe each weight, and then is the number of weights. How does the training works with MoMos? There is an initial backpropagation step that occurs as usual. It can be Adam, SGD, or some other method. After that, the vector, the weights are sliced into blocks, into n blocks of size s. Then they are extracted. Then k motifs are extracted from the uniform distribution over the blocks, and the closest motif to which the index of the closest motif to each block is assigned as the index. Therefore, the final vector at the end of each epoch is reconstructed, and the training restart from the new value of W. In this way, W can be compressed in Z and M, in the motifs and in the mosaic. So, So let's go with some experiment to show how good this technique performs. For this experiment, I used the Cypher 10 with an MLP of about 1 million parameters, slightly less actually. I trained the model for 100 epochs. There is no early stopping. I use 5-fold cross-validation. It's also nice to introduce this capacity. the definition of the capacity. So in MoMos, there can be at most n blocks, right? I mean, the whole vector is represented by n blocks. So if the codebook has size n, then there is no constraint at all inside in the model. The capacity effectively is the number of blocks, the number of motifs divided by the number of blocks, where the number of blocks is the upper bound, and so it is the percentage of how much weight sharing there is enforced by MoMos. We report the compression ratio, which is a bit different from the capacity, and the compression ratio just shows how many times shorter the description length got. So yeah, on the left we have the test accuracy. Higher accuracy means better performance, better, yeah. While going to the right we have more compression, as it is very intuitive. The more you compress, the more the accuracy drops. The best models, the models that achieve the best accuracy are the models that has the smallest block size. Yeah, and in particular we can see that the weights, the performance are basically clustered by block size, but the more you reduce the capacity, the more the shape is sort of important. Yeah, for example, this 2-2, but 1-4 is better, and 4-1 is the worst one. Alright, so if the weights are in the same column, it's better. We will show this, we will explain this later on. Another thing that is interesting is that if you reduce the capacity too much, then a bigger block size with some higher capacity is going to perform better. You see, for example, with a block size of 4, there is this blue, pink, and orange, and then a block size of 8 dominates all of them, even if the because the capacity is higher. I trained the MLP, one MLP with block shape of 1, 2, which means block size is 2, as there is 1 row and 2 columns. And after 400 epochs, we see that the motif usage concentrates on very few motifs. There is some sort of long tail distribution. Since the block size is 2, it is also possible to scatter plot the motifs. So on the X there is the first weight of the motif, on the Y there is the second weight of the motif. In this case I'm comparing the different block sizes, the block shape. So there is here we have 2 weights in column, here we have 2 weights, 2 weights in row, 2 weights in the row, 2 weights in column. So across multiple rows, across multiple columns. And as training goes, we can see that for the shape 1, 2, then the motifs line up, while for the shape 2, 1, motifs tend to cluster. So the dynamic is not that far away, but here there is a clear line, and we think that this is because the dataset is cipher and motif weights are contiguous when the block shape is 1, 2, and so they are weights of the same neuron referring to contiguous pixels, while here they are weights of different neurons on the same feature. And so it's reasonable to assume that pixels that are close together in the picture have similar values, and so their importance for that neuron is going to be similar, while different neurons on the same picture are more independent from each other. But there is some kind of organization, and this is just after 200 epochs. After 400 epochs, we see that the weights get even more sparse. There is still some kind of line here, while here they are sort of less clustered. Indeed, they go up to 8,000, while here they go up to 5,000. So here motifs are much more clustered compared to here. But it's also interesting to see that the motifs actually are inside each other. They somewhat converge to some motif, and they become inside of each other. And here it is basically the same. You see, there are a lot of motifs all inside of each other. Yeah, this brings us to notice that basically there is a hard constraint that is enforced from the very first epoch, and then there is a soft constraint that is given by the projection and the redraw of the codebook, the continuous redraw, which at the end of the training basically converges toward a much more constrained hypothesis class compared to the initial one. I mean a hypothesis class that has way less motifs. This means that a lot of motifs at the end of the training can even be discarded to compress the model further. Just to provide an overview of how breakdown of the bit consumption, we see that the mosaic dominates the memory of the representation of the description. Here we can see the motif, but otherwise the blue line that is the complexity of the motif we cannot really see it. Therefore, we introduce V-Fold MoMos that tries to compress the mosaic further. So an easy attempt to improve, to reduce the description length of the mosaic is to grow the block size. Otherwise, you can try to apply MoMos on top of MoMos, so some kind of recursive approach. And this is exactly what we try to go with. The idea is that we restrict the number of motifs that can be indexed at each block position. So we have the weight, the vector that we want to compress, then we have the codebook, and we introduce a partitioning on the blocks so that here to simplify we use a block size of 1, but it doesn't matter, it can be a bigger block size just to have a simpler picture. The blocks are partitioned, and so the first block is assigned to fold 1, the second fold 2, the third fold 3, and it repeats in a periodic fashion. And then the motif, the blocks that belong to the first fold can index only the motif in the first fold, while the blocks that belong to the second fold can index only motif in the second fold, and so on. In this way, the index map gets halved. Like generally, we don't really halve the index map, but in this case, like in this specific case, it is because you would need 2 bits to index 4 motifs, but here, since there is this indirection, you only need 1 bit to index each motif in the fold. And notice that the sigma the sigma function is also a constant function, a constant size function, and so it doesn't cost in terms of Kolmogorov complexity. Yeah, you can also consider this technique as using sigma to partition the blocks into folds, and then you apply a MoMos parameterization in each partition, but you constrain all the different MoMos parameterization to have a shared global codebook. Yeah. So how does the bound on the Kolmogorov complexity change? We introduce the complexity of the folds, which is the complexity to index. Yeah. But we reduce complexity in the mosaic. So as long as we remove more bits from the mosaic, we can use more bits for the folds, and there is some sort of equilibrium there. Yeah. So now we are introducing a lot of new parameters, and it's a bit hard to find the best parameterization and so on. So I used log₂k to with some genetic algorithm to identify the best the Pareto front. I used also quad, a naive quantization approach that is employed throughout the training to compress the neural network, and yeah, I tried to apply MoMos and full MoMos on ResNet and MLP for 100 epochs without cross-validation in this case, but I repeated the training with cross-validation. So an interesting thing to say is that V-Fold MoMos does not appear in the Pareto front of ResNet, which might mean that the constraint that is given by V-Fold MoMos is too hard, but also the CNN has a very strong inductive bias, and so yeah, it is what it is. ResNet 20 is also 5 times smaller than MLP, than the MLP that we are training. Yeah, the MLP is also much more compressible. We are able to compress it by 40 times, losing 15 in accuracy, while we don't even reach 20 and we lose. It's also interesting to notice that in this case the stars are the MoMos parameterization, while the squares are the V-Fold parameterization. And yeah, if you make a line pass through the MoMos parameterization and make a line pass through the V-Fold MoMos parameterization, they are basically the same line. I did another breakdown, and here again we see that also with V-Fold MoMos the mosaic is still dominant, so we need some other technique to actually reduce the complexity of the model. For example, we saw before that the motifs are very concentrated, so some half-man encoding can be very useful. Regarding the VC dimension of MoMos, so we have this idea that bigger model implies better performance, but it's quite hard to formalize it in proper terms. So the hypothesis in this case is that higher Kolmogorov complexity implies better generalization, and hopefully there is a math formula that can predict how generalization changes with MoMos parameterization, so as a function of the number of motifs and the block size. Now, what is the VC dimension? VC dimension is H shutters and points. Yeah, VC dimension is the biggest size that is shuttered by a hypothesis class, where basically you can assign random what do you say? A random label like plus, plus, and minus to each of the point. If you can divide the point, for example, say up is positive, down is negative, then you can shatter them. Cover did some amazing work in this sense, and he proved that a linear model, so a line where the sign provides the class, has a VC dimension of 3. How does it change for MoMos? So the proof, I think, is fairly easy in its term. Yeah. So to preserve shattering capabilities, k should be bigger or equal to 2 to the power of s, or to the number of blocks. So number of blocks is quite trivial, as we showed before, but this is an interesting result, because if we consider s to have a size of 1, and then k has to be bigger or equal to 2, and this shrinks the model by a huge amount, very, very big. And yeah, the thing is, the tricky thing is that actually MoMos is a union of subspaces, of linear subspaces. So you can think, let's take, I like the MoMos picture. So considering this picture, effectively the codebook defines the linear subspace, also the size of the linear subspace of the parameterization, while M defines the permutation on the linear subspace. Basically defines how you can orient, how you can turn around the parameterization. Yeah. Yeah. So, for example, we can present the VC dimension on the plane. If we define, no, if we use the MoMos parameterization with a block size of 1 and 2 motifs, then these 3 are the 3 family of lines that remains inside the hypothesis space. And as it is shown by this small drawing, we see that the shattering capabilities, the VC dimension is preserved, just like the theorem says. And even if the degree of freedom of each individual family is 2. And so the VC dimension of the individual families is 2, but the union of them is 3. So long story short, MoMos bounds the Kolmogorov complexity during training, and motif cluster and converge throughout the training. So there is a sort of collapse of the motifs. Yeah, we have also shown that the mosaic dominates the complexity of the parameterization, both for MoMos and V-Fold MoMos, and preserving the VC dimension, and MoMos quite easily preserve the VC dimension, while it loses the capacity. Like, by definition, the capacity is given by k times s, and so for MoMos, the capacity is exactly the definition of capacity that we given before. K times S, no. No, it's not the fraction of it. Yeah. So the key takeaway is that redundancy reduces complexity. Regarding future work, as we shown, the mosaic is the most complex part of the description, and some entropy code can be used to reduce the complexity of the mosaic. So you use less bits to encode mosaic that are very used, and as we show at the end, especially at the end of the training, the distribution of the motifs is a long tail, so this can save a lot of bits. Then we can think to describe the motifs using some kind of function similar to hyper compression, the paper that I referenced at the start. And V-Fold MoMos has I think that V-Fold MoMos is very interesting because it creates a codebook that has a fixed size, and then you can have different parameterization that compress the model further. So for example, in a distributed approach, you can share just the codebook, and for example take the average of the various codebook, while the mosaic remain on every node, and then you also synchronize the mosaic much more rarely, so that the motifs themselves don't collapse or reach a better solution at the end of the training. And also, especially, we showed that the motifs, the codebook, the global codebook itself is incredibly small, so it's very easy to share in a distributed fashion. So yeah, thank you so much for listening to me so far, and yeah, let me know if you have any question. Yeah, I don't know. Maybe I will provide some email or some way to reach out to me at the end in the description of the video. Thank you so much.